In this video, we discuss quorum systems. Before we explain what quorum systems are, first a little observation. If you study distributed protocols, you will often observe lines of pseudocode like these. If a majority of servers does something, then something happens. These two lines are taken from the classic Paxos protocol, but they appear in many other protocols. Where does this obsession with majorities come from? This is a good time to pause the video and see if you can figure out the answer yourself. Here is a distributed system with 5 servers. The reason distributed protocols do not want permission from all the servers is simple. Some of the servers may be down. If a protocol always had to wait for all the servers to make progress, that would be a disaster. Any single machine being down would halt our whole system. One important promise of a distributed system is to make progress even if some of the servers are not responsive. But why do we ask for a majority of servers to reply? Assume we have a protocol which only needs 2 servers to answer to make progress. Let's say a red client gets permission from 2 of the 5 servers. Assume that concurrently a yellow client also gets permission from 2 servers. In this case, the red client and the yellow client operate completely independently. This could be a problem if the red and the yellow actions interfere in any way. For instance, if both clients want to manipulate the same data. However, if both clients need to have permission from a majority of servers, 3 in this case, then it is guaranteed that they have at least one server in common. This is the main reason why so many protocols use majorities. Quorum systems study such overlapping sets in a more formal way. When studying quorum systems, we are given n servers, sometimes we also say n nodes. In our example, n is equal to 5. A quorum is any subset of these 5 nodes, like this, or like this. A quorum system is a set of these quorums, such that any 2 quorums in the quorum system overlap. In other words, any 2 quorums share at least one node. So this is a quorum system with 5 nodes and 2 quorums. Let's make another example to make the definitions clear. We again have 5 nodes in our quorum system. Let's add a bunch of quorums, first a yellow quorum, then an overlapping red quorum. Now let's add a green quorum. You see that the green quorum is smaller than the yellow and red. This is okay, there is no restriction how big a quorum needs to be. All we need is that any 2 quorums overlap, and the green quorum does overlap with both the yellow and the red quorum. Let's add 2 more quorums, a gray and a purple quorum. Are you happy with this quorum system? Please pause the video and think about it for a second. As you probably noticed, this is not a quorum system as the green and the purple quorum do not overlap. Our image is a bit messy, but if you look carefully, the green quorum consists of the nodes 1 and 2, but the purple quorum consists of the nodes 3, 4 and 5. So there is no node which is both in the green and the purple quorum, and hence this is not a quorum system. So let's remove the purple quorum to make it a correct quorum system. You may think that this is still not a very good quorum system because the red quorum is just a subset of the gray quorum. In other words, the gray quorum has all the nodes of the red quorum plus some more. This is also true for the green and the gray quorum. If one quorum is a subset of another quorum, the quorum system is not minimal, and we generally prefer minimal quorum systems. So let's remove the gray quorum. Now our quorum system is minimal, since no quorum is a subset of another. To analyze quorum systems, we introduce one more concept called the access strategy. The access strategy simply specifies a probability for each quorum. This probability says how likely a client is to access the quorum. For instance, clients might access the green quorum with 50% probability, the yellow with 30% and the red with 20%. Given a quorum system, we can compute 2 important measures, the load and the work. Let's start with the load. The load of a node is the probability that the node is accessed. Node 5, for instance, has load 20%. It is only in the red quorum which is accessed with probability 20%, so node 5 is also accessed with probability 20%. All other nodes have a higher load in this quorum system. The node with the highest load is node 1, which is both in the green and the yellow quorums, and as such accessed 80% of the time. The load of the quorum system is the highest load of any node, so in this case the load of the quorum system is 80%. If you change the access strategy of this quorum system, how much could you bring down the load? Please pause the video and try to find the best access strategy. In this case, the best would be to access each quorum with the same probability. The probabilities must sum up to 1, so we would access each quorum with probability 1/3. Then the load of the nodes 1, 2 and 4 would all be 2/3, which is the best possible. The work is defined per quorum and simply measures how many nodes are in that quorum. So the work of the red quorum is 3, and the work of the green quorum is 2. The work of a quorum system is simply the average work given the access strategy, so how many nodes a client needs to access on average. Since the green quorum is accessed half the time, the work of this quorum system is 2.5. We could improve the work of the quorum system if we accessed the green quorum more often. But this would make the load worse. There is usually a trade-off between load and work. Let's say you only care about work. If you could freely design a quorum system, what's the quorum system with the minimum work? Please pause the video and think about this for a second. Well, this was a bit of a trick question. To minimize work, we want as small quorums as possible. The smallest quorum is just a single node. To make it minimal, we can only have one quorum in our quorum system. This is equivalent to just a single central server doing all the work. Let us summarize this video. We learned that quorum systems are made of n nodes, and a set of quorums such that any two quorums overlap. Our example quorum system had 5 nodes, and on average we had to access 2.5 nodes, while the most accessed node was accessed 80% of the time. On the other hand, if we just have a single server, we have a system with just one node and also work and load of 1. A very common quorum system is the majority system with n nodes. Every quorum is a little bit bigger than half the nodes, so the work is roughly n divided by 2. Every node is in about half the quorums, so the load is roughly 1/2. Thanks for watching this video.